Greetings, everyone. We're excited to be here with you today at Hacking the Box. This is holding the stick at both ends, fuzzing the RDP client and server. We'll start with a quick word about ourselves. My name is Reiner. I am a security researcher at CyberArk Labs. And with me today, I have Porath, who is also a security researcher in our group. And we're here to tell you about our journey into fuzzing RDP. Our agenda for this session will be as follows. First, we're going to talk about our motivation going into this project. We'll also provide some of the basics needed in RDP in order to get fuzzing started. Then we should jump right into the deep end and start to build our fuzzing environment from the ground up. We'll also try to explain what made this fuzzing target quite unique and how we were able to overcome the challenges that we faced until we were able to fuzz it finally. After that, we will talk about the results of our journey. We will also dissect one of the issues that we were able to find in RDP. And finally, we will have the mandatory summary slide, and we should also discuss some future work opportunities. So without further ado, let's go right ahead and start with RDP. So this is what the end user usually knows as RDP, or the Remote Desktop Protocol. We probably all know this flow by now. You need to access a remote Windows machine. So you fire up mstsc.exe and you're ready to go. It's pretty simple. But as we are soon to find out, there is plenty that is going on behind the scenes in order to make this remote connection possible. But before we get into that, let's talk about the motivation. So using a simple shotgun query, we see that there are almost 4.5 million RDP servers exposed to the internet. And as you may imagine, there are plenty more behind different firewalls or inside some internal networks or something along the lines of these. So RDP is widely used by Windows users for their remote access purposes. But how can this serve an attacker? Mainly, there are two attack vectors for attacker. So the first one is the more traditional in a sense, and in this one, the attacker is trying to get access into an internal network. There is an RDP server in that network, which is exposed to the internet. But of course, the attackers don't have any credentials for it for obvious reasons. So the attacker can exploit a vulnerability in the RDP server and use it in order to gain access, unauthorized access to the server, and from there to the entire network. As for the second vector, it is not as common, and it targets the RDP client rather than the server. Here we have an attacker who was already able to gain access to some sort of a server or a virtual machine inside the network. And they can wait for an administrator to connect to the server, then exploit a vulnerability within the RDP client this time, which will allow them to gain the administrator's privileges and execute code on their machine. So this is the second vector. Now, these are not merely theoretical attack vectors. There have been some real-life examples for both of them in the last few years. And to name a couple, Deja Blue, which was an integer overflow bug in a decompression function in the RDP server that allowed attackers to run arbitrary code remotely. And for the second vector, we had reverse RDP, which was a path traversal bug in Microsoft's RDP client that allowed an RDP server controlled by an attacker to run arbitrary applications on a client that is connecting to it. So these are the two examples that we give. So we can agree that RDP can be a lucrative target for attackers. But why do you think we should fuzz it? To answer that, let's have a quick look at the RDP attack surface. And as you can see from this simple file listing query in PowerShell, on a vanilla Windows installation, we have more than 190 RDP-related libraries, drivers, executables, and so on. So it's quite a lot of code. And at this point, manual review doesn't really sound like a great option. And this is why we chose to go with fuzzing in this case. But before we can start fuzzing, we need to understand some basics about RDP, or the Remote Desktop Protocol again. So naturally, we go and we try to read the docs. And after you download the relevant file from MSDN, you can see that you have around 30 specification documents with hundreds of pages in each of them. And sadly, not a lot of pictures. And as you can see clearly, we have a lot of reading material. So we should try to boil it down to the absolute essentials for us before we get into the fuzzing. So RDP is indeed a complex protocol. It relies on several layers of protocols and standards in order to be able to function and operate. It runs over TCP usually, although UDP is also an option. And it uses, as you can see here, TPKT, X.224, and T.125 MCS for data encapsulation. That's quite a mouthful. So this is the protocol stack of RDP. Now, an RDP connection has some general features that define it that we thought should be worth mentioning. The first one is negotiation. Many of the connections functionality can be negotiated between the client and the server. And these are things like the security level of the connection, the encryption and compression algorithms that are being used in the connection, the supported audio and video formats, for instance, and many other things that are negotiated. So the client has some sort of an effect on how the connection will look like because of this negotiation scheme. Other than that, RDP also have data compression. So in some of the layers of RDP, the data being sent is compressed by the sender and later decompressed by the receiver. Compression code can be erroneous many times. So having a lot of data compression logic in our target is really a great thing. And this is, of course, from the attacker's standpoint. And again, for example, Deja Blue from that we mentioned before was a decompression issue. Next, we have also security in RDP. So the protocol has some security features built into it. So for example, it mandates some sort of data encryption level to be activated. And it makes the protocol somewhat secure at the base level. So these are the general stuff that you should know. Now let's have a look at the following diagram and get a little bit more specific about RDP. So I like to refer to RDP as a protocol of protocols. And I think the first one to coin the term was Malware Tech in one of his blogs. And I've been using it since because it's really kind of true. So as you can see, an RDP connection is comprised of multiple different channels. And here in front of you, you can see different types of those channels. So from the top, first we have static channels, which are being opened in every connection, no matter what. They are basic and essential for RDP. Next, we have virtual static channels, which are an extension to the static channels. And those are optional, meaning they are negotiated in the initialization of the connection. And finally, we also have the dynamic virtual channels that can be created and destroyed upon request throughout the connection lifetime. And those are encapsulated within one of the static virtual channels that we saw before. So each of those channels serves a different purpose. So you can have the user input channel, a display monitor output channel, an audio channel, and so on, and many, many more. And every channel has its own initialization sequence, message types, data structures, and this essentially makes it its own protocol, and hence we call RDP the protocol of protocols. So here you can see an overview of the actual software components at play during an RDP connection. So let's start from the right. You can see here we have the client. We have mstsc.exe, and it loads the mstsc AX DLL, which contains most of the protocol logic handling on the client side. And of course, as you can imagine, this makes it a huge binary with almost 19,000 functions. And from the screenshot, you can see that at least we are lucky enough to have public symbols for most of those functions. So at least we have that. So this is the client. Now, on the other side, we have the server. And again, just to mention that because of the fact that the mstsc-AX DLL has so much code in it, this is yet another reason to go with fuzzing in this instance. Now, to the other side, we have the server. The server has a main service, which is hosted inside SVC host with the term srv.dll. It also loads several other DLLs. An example for those you can see here that handle the protocol logic on the server side. Other than that, the server also runs a few other processes that handle different channel information. For example, you can see here the RDP clip process, which handles clipboard information. And finally, the server also has a few kernel modules that it loads in order to handle some channel functionality. And for example, you can see RDPDR here, which is responsible for device redirection from the server to the client. So these are our software components. And now let me hand you over to Or to continue and talk about fuzzing.
Okay, so now that we have some understanding of RDP and how it works, let's start talking about how to fuzz it. But before we do that, we need to talk about fuzzing in general. So this is a classic setup of what fuzzing looks like. So what we have here is we have the target process on the right. We have a fuzzer that generates test cases and inputs them to the target. And we have the code coverage engine that tracks the execution flow of the target and reports it back to the fuzzer. So in this example, what we can see is the target is the PDF reader, and the fuzzer generates the inputs, which are PDF files, and opens them using the reader. So this is pretty straightforward. But when we talk about fuzzing RDP, how should the fuzzing setup look like? We can't do something exactly like that because first, we have two machines. Fuzzing runs on two machines. We have the client and the server. And second, we don't have a clear option for what the input files are or anything of that sort. So what can we do? Okay, so let's see what we came up for fuzzing RDP. The first thing we had to figure out is how can we even send inputs to our target, whether it is the server or the client. So when we started the project, we had a few options. The first one was to take an open source RDP client or server and modify it so that it will send our fuzzing messages. The second one was to write everything from scratch, write our own client or fuzzer, and use that to send our inputs. The third one was to use snapshot-based fuzzing. Now, snapshot-based fuzzing has the advantage that you don't really need to recreate the connection every time. Basically, you just go back to the snapshot, change the input in memory, and continue from there. And finally, we had the option of living off the land, meaning we tap into some existing RDP connection and use exported APIs or code injection to send our fuzzing messages. And eventually what we did is, for the client side, we decided to use existing solutions. And the reason we did that is because the RDP server exposes very convenient APIs that you can use to send messages to the client. And for the server side, we chose to modify an open source, namely OpenRDP, and you modified it so that it will send our messages as well as the regular messages. So here's the basic idea of how fuzzing the client looks like. And let me just say that the credit for this architecture is to Park, Yang, Kim, and Lee from Korea University. And you should really check out their Black Hat talk from 2019 that we linked here. Now, what we can see here is on the right-hand side, we have something very similar to what we had in the classic fuzzer. So we have our target, which is the RDP client, and we have the fuzzer and the code coverage engine as before. Now, the main difference is in how the input messages are sent from the fuzzer to the target. And the difference is that the input messages are first moved from the client side to the server side, and then an agent that we wrote takes this message and sends it over to our target. So it looks something like this. And let me just remark that the basic idea is the same for the server side fuzzing. We just basically mirror the image. Now, we did some optimization, especially for the client side, and we ended up with something like this. So the first thing you should note is now there is just one machine. And what we have is that, again, that on the right, we have the target function, which is now mstsc.exe. And we have our code coverage engine, which is using DynamoRio and WinAFL. And we have our fuzzer, which is AFL fuzz. Now, the main difference is that instead of connecting to a server side, we are just connecting to localhost, to the same machine using RDP. So we can run everything locally, and we don't need to send the input messages from one side to the other. So we just send them to the agent, which runs on the same machine, and it sends it over to the target as if it was from the server. Now, the upshot of that is that we can have multiple instances of the same fuzzer and target on the same machine. So we ran concurrently 10 fuzzing instances on the same machine. Okay, so the next thing we did is we chose what are we even fuzzing? What are we sending? Because practically every channel, as we said, is its own protocol, we chose to fuzz what we call channel by channel. So every time we would pick one channel and we would fuzz that independently. And because for the most part, channels are their own protocol, we can cover most of the logic of a channel just by fuzzing it alone and disregarding everything else. Now here I will make a technical remark. When we tried to fuzz the server, we had a bit of a problem because the server is it runs on a process, a service on the system that runs from the boot of the system. And in classic fuzzing and in DynamoRio and WinAFL solutions, the fuzzer has to control the creation of the target process. So in order to overcome it, we had to add a functionality to DynamoRio that will attach to an already running service. And this is kind of tricky because there are many places you can fall about threads that are already running and might be terminating when you take over them. In any case, we took an existing pull request and that was never merged into the code of DynamoRio, and we made it work. We added some functionality on top of it. And let me just say that if you find any of this useful, you can use our DynamoRio build from our GitHub page that we will add in the end of the talk. Okay, So now that we have a connection and we know how to send messages, we come into the first problem. When we take over a live connection, there are many messages that are sent from the client to the server and back that have nothing to do with the fuzzer. This is a live connection. There's lots of data going from one side to the other. And we need to find a way to differentiate this data from the messages that we sent as part of the fuzzing process. So this would look something like this. What you can see here is there are a few normal messages that are transferred on the connection. And the last one is our fuzzing message. This is a test case that was generated by the fuzzer. Now, in order for coverage-guided fuzzing to work, there must be a one-to-one correspondence between the inputs and the code path that they triggered. So to do that, we developed what we call background fuzzing. That is differentiating our fuzzing messages from the regular messages of the connection. And we need to only track code paths for the former, for our messages, for our fuzzing messages. And again, this is essential because if we track code coverage for the rest, then the fuzzing is completely ineffective. Now, the way we identify the fuzzing message was by adding a marker. So in this example, the marker is the first byte that you can see in red. So the agent, the fuzzing agent, has changed the marker to this EXA-FF instead of the typical EXA-20. And the target detects it, and it restores it to 20 before the execution, before the message is actually handled by the target, and that allows us to identify the different types of messages. So let's take an example. Here we can see the documentation of the RDP sound virtual channel. And this channel is used to redirect sounds from the server to the client. Now, according to the documentation, the first byte of every message is the type of the message that is sent. And the supported values for these message types goes from 1 to EXA-D. Now, what we can do in this case is we can use the most significant bit of the first byte as our fuzzing marker. So we do something like this. The agent will turn on the most significant bit of the first byte before it sends the message. And WinAFL on the other side will check if the most significant bit is on or not. If it is on, then it knows that this is our fuzzing message, and it will turn it off. It will turn it back off so that execution completes normally, but it will track code coverage for this. And if it is off to begin with, then we can just ignore the message. This is a background message. It has nothing to do with the fuzzing. Okay, so now that we have that, we have the basic ability to fuzz, to send our messages. We differentiate them from the background messages. And we started fuzzing. And we came up across the following problem. Basically, whenever the target found out that there were 2 consecutive bad messages, it would simply close the connection. Obviously, this is horrible for fuzzing purposes, and we cannot allow it. So we had 2 approaches of how can we get around it. The first was using code patches. Simply avoid this, do not let the target close the connection. And the second one was grammar enforcement, meaning only allow the fuzzer to send messages that are valid enough to not close the connection. So let's talk about them for a bit. First, we will talk about code patches. So code patches are simply avoiding these paths in the code that are bad for us, that terminate the connection. So this is an example from the graphics channel. And what you can see here is that it checks some condition, and according to that condition, it either exits the process, or it logs the error and it reconnects and tries again. And what we did is we patched the conditions so it will always choose the path of logging and reconnecting, so it would never terminate at this point. And let me just remark that Dynamo Rio exposes a very nice functionality that allows you to do it very easily. So what you can do, basically what it allows you to do is to take one address, and whenever the target gets to that address, it will just skip to the address you supplied. So we have this original target and the replacement, the original address and the replacement address. And we simply say that if we get to the bad path, just jump to the correct path that we want. Okay, now let's talk about grammar enforcement. Grammar enforcement, we used it to enforce the size that we allow the messages to be, and the values and the visibility of some of the fields that are in it. And the question is, well, how do you find what is valid and what is not? So we did it in the following way. First of all, we looked at the documentation. When all else fails, read the docs. And Microsoft has great documentation about RDP, and we extracted most of the grammar from it. But in some cases, this wasn't enough, so we reversed engineered the actual code, and we saw what the conditions are and how do we get to the failing conditions. And lastly, we just, when everything failed, we had to trace our errors and find what condition actually caused the errors and fix them. Now, an important note about grammar enforcement is that it limits the space of possible test case that the fuzzer can generate. So this means that we basically limit the fuzzer in what it can do, and therefore we can miss some interesting inputs. And for that reason, what we tried to do is to enforce as little as we could, but still ensure that the connection is not closed too often. All right, so now we have a running fuzzer. It sends messages, we detect them as we want. But after some time, we found that there was not, our coverage was not big enough. And what we realized is the following. What we had is every message for itself. We had a single input messages. So the fuzzer would create test cases, and each test case is a single message. And we realized that the reason we had low coverage is because a lot of the logic of the RDP channel depends actually not on a single message, but on a sequence of messages. And what we decided to do is to make the fuzzer create larger test cases that are actually a sequence of messages. So it would look something like this. The first test case would be, say, 3 messages, and the second would be 2 messages, and so forth. So let's give an example of why this is important. So here we look at the graphics channel again. And what we have here is we have this map surface to output PDU. And PDU is the protocol data unit, so it's the basic message. And what it does, it maps a predefined surface to the output buffer. But as you can see, it accepts a surface ID that has to be provided to it. And that surface ID should be created before that using the create surface PDU. So it makes no sense to send a map surface to output PDU without a previous create surface PDU with the same ID. So that's why we needed this multi-input fuzzing, because to reach the interesting code paths that happen as a result of the map surface to output PDU. So what we did to implement this is we used a WinAFL feature called AFL Dictionary. Basically, AFL Dictionary allows you to define a sequence of bytes that the fuzzer will try in its mutations. So you're basically telling it from time to time, instead of just trying something random, try this sequence of bytes. And what we did is we used it to separate protocol messages. We suggested the fuzzer would use the keywords underscore, 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 command, whatever, command number of the command. And we would use that in the agent to split the messages. So the test case would look something like this, and the agent would split it according to these keywords in this manner. So this will be 3 messages, message with command type 7, then 2, then 3, etc. Now, an important note here is we need the fuzzer to complete the fuzzing iteration only when it receives the last message in the sequence. And to do that, we used what we already discussed. So we added a second marker that tells tells WinAFL that we have reached the last in the sequence, and only then will it complete the fuzzing iteration. All right. So now we have a fuzzer that runs and it sends multiple messages. And in some cases, we had to deal with multi-channels. So although we said for most channels, they are completely independent, that is not correct for all of them. So this is an example for the video extension of RDP. And this extension works on 2 different virtual channels. One channel is for the control messages, and one is for the actual video data. So what you can see here is that the first 2 messages are sent over the control channel. Basically, the server telling the client, hey, listen, I'm going to send you some video data. And the client says, sure, go ahead. And then the actual data is transferred on a different channel. So here we needed to somehow send multiple messages on 2 different channels. And we did it in a very similar manner. Basically, we split the messages as before, but the type of the message also told the agent on which channel it should send the message to the target. So for example, here, say a message of type 7 should go to the control, message of type 2 should go to the data, and message of type 3 should go to the control again. Okay, so now we have almost everything, but we had some basic challenge, and that was actually finding where the target function is. Meaning the code base for RDP, as we saw, is huge, and it's hard to locate which code actually deals with the messages that we're sending. So to do this, what we did is we downloaded every PDB that was relevant to RDP, and from it we extracted all the function names, and we inserted these names into a small database that links a function name to the binary it runs in. And what we found that really helped us speed things up is that typically the target function had the pattern C class name, so say, I don't know, graphics client channel, on data received. So what we did is we grabbed all of those, and that gave us a list of candidate target functions that we can scan through and see if any of them are relevant to the messages that we're sending on a given channel. And let me just make a side note that it would be very helpful and very interesting to have a database of all available info and function names of all public Microsoft PDBs. And we didn't get around to it, but if someone wants to take the challenge, we think it will be very beneficial for the security field to have such a database. Okay, so a few fuzzing iterations later, we found our first crash. Hurrah. But alas, we had some more issues. So we started getting crashes, but what we did is we took those inputs that generate the crashes and we tried to run them on a clean machine without the fuzzing environment. And unfortunately, some of them did not reproduce. They would simply not crash. And our assumption was that it has to do with the state of the protocol at the time of the crash. So basically, some previous message put the connection in the right state, and then the crashing input would crash the target. So we had to come up with a solution that will allow us to understand crashes even if we cannot reproduce them. And we came up with the following. So I know this looks scary, but don't worry, it will be fine. Basically, what we had is we had this watchdog in the middle, and every time the target would crash, the watchdog would detect it, and the target will hang until the watchdog had time to create a full memory dump of the target. Next, we had a PowerShell script that sampled this folder and used the windbag script to automatically analyze the dump and find the crashing call stack. Now, this is not completely trivial because the crash, we had to analyze some Dynamo Rio structures to find the actual call stack. But after that, we have the call stack of the crash. And what we did is we would check it against previous call stacks. And if it is new, we would alert ourselves and send us an email telling us, hey, you got something new, and let's check it. And we know it is a bit hacky, but we came here to hack, and besides, it worked quite well. So this is what the exciting email looks like. Here you can see a crash in a audio channel, and you get that, you're very happy. Now I will let Shaked talk about the results.
All right, let's talk about results. So in front of you, you can see an example for one of the stat screens of AFL for one of the channels that we've fuzzed. And you can see here that the execution speed is not that fast, to say the least. However, the fuzzer did manage to find some crashes that we can work with. And if we take a look at an overview of the numbers, we were fuzzing for around 1 month, and this is actual fuzzers running. We fuzzed 15 channels in both directions, the client and the server, and we were able to find 5 bugs in RDP. So now I will dissect one of those bugs for you, and we can see and we can better understand what those types of bugs look like. So this bug was found in the audio playback channel. And what is this channel? Basically, it just redirects sounds from the server to the client. So the client can hear whatever's going on the server side. So it all started with this crashing stack, as you can see from this windbag screenshot. And as you can see, the crashing function was on wave data. And if we take a closer look at the crashing input that caused it, we can see this. And here, this is a good example for why the multi-input fuzzing that Or talked about was helpful in the RDP case, since this particular input that caused the crash involves 4 different PDUs or 4 different protocol messages, as you can see. All right, so naturally we'll go to the crashing code and try to understand what's going on there. And after we clean up the pseudocode a little bit, this is the crashing function. So based on the crashing stack, we know that the crash happens in the last line of code here, where we have the access to an element inside the formats array. And now we should try to understand a little bit better what this array is all about. And before we dive into understanding what triggers the crash and what is this array, let's have another high-level look at what may a legitimate flow in this channel look like. So first we have the server, which sends a list of the sound formats that it supports to the client. Now, when the client gets it, it creates or it allocates an array containing all of the details on those sound formats for a later use when it will need to process sound messages from the server. Then the server is basically free to send sound information in any of the formats that were announced before. And finally, the client uses the format index that it gets from the server in order to access the format array and process the data. So in this example, you can see that in the first message, the server announced an array of 3 supported formats, and then the server used the third format in one of its data packets of sound. So this is a legitimate flow. Now, based on the crashing input, we can understand what happened before the crash. So let's see how it goes. So much like in the legitimate flow, the server sends a list of 3 formats that it supports. Then the client allocates an array for those 3 formats and stores the information there. After that, and again, this is like the legitimate flow, the server sends some data in format 3, and the client processes it pretty normally. Now it gets interesting. What happens next is that the server updates the list of supported formats, and this time with a list that contains only 1 sound format, practically causing the client to free the format array of 3 sound formats and to allocate a new array with only 1 sound format. Next, the server sends some sound information message with format 3 again, even though the client now only has 1 format to work with. And as you may imagine, the client tries to access the third format inside of an array of only 1 format, and practically causing it to crash. So if we have another look at the function we saw before, the crashing function, we can understand the flow a little bit better. So this is what happens here. In the first couple of lines, the client simply reads the format index from the message. Nothing too special about that. Then the client checks whether the sound format is different this time from the one that was previously used by the server. Now, if it is different, the client will then treat the format change, and this of course includes some bounds checking for the array. So the client will make sure that the new format index is within the bounds of the format array that it has. So this is if it's different, and then it will process the data with no problem. Now, in case of the format being the same as the previous packet, the client will simply access the array in the appropriate index and will continue to process the data as if nothing happened. As you might have guessed already or understood already, the issue is that the bound check occurs only when the format has been changed by the server. But our crashing input didn't change the format, it changed the array itself, practically making it smaller. And this is what ultimately caused the client to crash. And so now that we understand this, you can see how this type of bugs look like. Now, this is an out-of-bound read bug with a limited impact, but we still feel that it is a good example and it demonstrates well how effective the multi-input fuzzing was, and also what RDP bugs may look like. All right, so let's try to summarize what we've learned today. The first point we believe is worth making is that really nothing can be deemed as unfuzzable. This project shows that no matter how complex you think your target is, you can always find a way around it, and finally you will be able to fuzz it. And this is especially true with newer snapshot or emulator-based fuzzers, like, for example, what the fuzz by overclock. Those will be really great tools to try and fuzz some complex targets. And also, just let the fuzzer do the work for you. You don't really want to put in the effort to manually analyze the target, right? What's the fun in that? So really, fuzz everything you can. All right, regarding future work in this field, we believe it's worth putting more effort into fuzzing RDP. Our project was limited, of course, due to some circumstances, and it can be improved upon. And also due to the huge code base that RDP has and the large number of logical channels, we bet that there are still more stuff to find in RDP. We may go back to pursuing it in the near future, but we do encourage the community to join in on the effort. The other thing is that the platform that we've built around fuzzing RDP can be directed at a completely different target. By platform, I mean the multi-input fuzzing, the attaching to Windows services, and all the stuff that Or talked about. And this is exactly what we started doing. We started fuzzing some RPC server on Windows, and we got some promising preliminary results. So expect to hear more about that in the future. And also, what we've done is that we pushed all of the code and the tools that we used and modified to GitHub. You can find the link here below. This is the link, and it should be up there as we speak. If not, it will be in the next few hours. Again, you can find there all the stuff that we talked about. Just a disclaimer, it's not an off-the-shelf, ready-to-use type of situation, but it can give you a jump start if you are looking to fuzz RDP or a similar target on Windows. So please, we encourage you to go ahead and use that.
Finally, let me say that we encourage everyone to use the techniques and the tools that we've used in any way you see fit and for every target, and we'll be happy to discuss anything fuzzing related. Please reach out to us, and the best place to find us is on Twitter. And that's it. Let me say thank you very much for joining us today. I hope you enjoyed this convention, and please contact us. Thank you again.